morning class and welcome to our lectures on sustainable energy technology. We have started our discussion on carbon capture and storage as a possible means of increasing the sustainability of fossil fuels and making fossil fuel based energy resources less CO2 intensive. So, before we begin the discussion of how to capture and store CO2, let us look at the utilization of CO2 in the industry. So, CO2 is not merely a waste gaseous byproduct of combustion. It has a lot of useful properties which makes it a very good fluid for many different types of industrial applications. For people who are in mechanical engineering example, will know about CO2 based gas welding technologies, right? And in many chemical processes as well, CO2 is necessary and you will get CO2 cylinders for such process systems. So, let us look at some of the important molecular properties of CO2 first. Its molecular weight is 44 grams per mole. Its critical temperature is 304.13 degrees centigrade, so which is around 31 degrees centigrade. Okay. So, here a certain point for those who are not aware of thermodynamics phase change, usually we have three phases of matter: gaseous phase, liquid phase and solid phase. So, if you heat up a solid, it eventually melts at a certain temperature and pressure to form liquid, and then the liquid, if you heat it up further at a given pressure, it again starts to boil at a certain temperature and becomes vapor or gas. However, if you continue increasing the pressure, a point comes when the differentiation between liquid and gas goes away. So, the pressure is continuing to increase on this side and the temperature is also increasing on this side. Okay. So, for example, here, what you are seeing here is, suppose you go this way, alright. Suppose you go this way. So, here pressure is around 10 to the power 0, so 1 megapascals. Okay. So, here for CO2, you are going from solid and heating up the solid at 1 megapascals slowly, and eventually the solid CO2, which is often called dry ice, forms into liquid CO2 at 1 megapascals, and the solid to liquid phase transition happens. Then you heat it up further and this liquid CO2 boils and produces the basic gas phase CO2. So, at 1 megapascal pressure, if you heat or cool CO2, you will get all three phases. You will get solid, you will get liquid, you will get gas. However, at lower temperatures, 0.1 megapascals. So, 0.1 megapascals is 100 kilopascals, which is approximately our atmospheric pressure conditions. Okay. Now, at our pressures, CO2 is of course a gas, okay, and it remains a gas for a significant amount of time, up to say around 205 or minus 78 degrees centigrade. So, this is around 200 kelvins or something like that. So, at that point, you have a direct transition from gas to solid. So, there is no liquid phase. This is called the sublimation process primarily, that you are moving from the gas phase to solid phase or solid phase to gas phase directly. So, the CO2, the vapor CO2 becomes solidified directly without shifting to a liquid phase. Okay. There is this triple point. Triple point is the temperature and pressure below which the liquid phase no longer exists, and you can have a direct solid to gas or gas to solid transition. Okay, this is true for many types of material, not just for CO2. It's just for normal temperature and pressure, this is what happens. But at high pressures, you will see you get liquefied CO2 as well as gas, as well as solid. Okay. However, if you continue to increase the temperature and pressure, you will get what is called the critical point. So, the critical point is around 73 bars. So, around 7.3 megapascals, and the temperature of the critical point is around 31 degree centigrade or around 304 degree Kelvin. Okay. So beyond this critical point, you no longer have a distinction between liquid and gas. So you have a supercritical zone here. Okay. So the distinction between liquid and gas exists below the critical point, but above the critical point, liquid and gas can no longer be distinguished. It becomes what is called a supercritical fluid. Okay. Because CO2 can be, by compressing CO2 to 73 bars at reasonably normal temperatures, you get a supercritical CO2. So CO2 can be easily converted to supercritical fluid at high pressures. So this is the critical point in that context. Okay. And the specific volume of CO2 at these pressures is 94 centimeter cube per mole. Okay. These are the triple point conditions here, 216.5 kelvins, and the pressure is 5 bars. Okay. So still higher than atmospheric pressure. Okay. This is the latent heat of fusion. So, and this is the latent heat of sublimation. Okay. So because CO2 can easily be converted into a supercritical fluid, this supercritical CO2 has certain properties that make it very good as a solvent and a carrier agent in separation technologies. So in many chemical industries, this supercritical CO2 is extensively used as a type of solvent in which you can dissolve different types of materials. Okay. And it can act as a carrier agent for these materials in these kinds of separation technologies. So if you are separating two materials, you dissolve one material in the supercritical CO2 and then gasify it back at lower pressures, and that material gets deposited. So that way you can separate that material out of a mixture. So this type of separation technologies uses supercritical CO2 extensively. Also, because CO2 becomes solid and exists as what is called dry ice at minus 75 degree centigrade at normal pressures, so dry ice is extensively used in refrigeration and food processing industry. So often nowadays if you order cold confectionaries like ice cream or other things, you will see that it will have small amounts of dry ice in it to keep it cool during the transportation. Okay. So this dry ice is nothing but frozen CO2 below the triple point. Okay. Because it's frozen, the temperature of this CO2 ice is minus 75 degree centigrade, and it keeps the material cold for a very long time during the transportation. So this dry ice is extensively used in refrigeration and food processing industry as a very good and relatively cheap cooling agent. Okay. CO2 can also be liquefied at moderately high pressure. So liquid CO2 also exists at reasonably moderate pressures and at temperatures between minus 78 degree centigrade and 30 degree centigrade. Okay. Liquid CO2 is an excellent heat transfer fluid and is used as a refrigerant in commercial refrigeration systems. In commercial refrigeration systems, you often need temperatures significantly lower than ambient. So like minus 50 degrees, minus 60 degrees centigrades. There, if you compress CO2 and convert it into a liquid CO2 at these temperatures, it becomes a very good agent as a refrigerant fluid. Okay. So commercial refrigeration systems use liquid CO2 as a refrigerant in many of their installations. So these are some of the primary uses of CO2 in the industry. CO2 is extensively used, but despite this, only around 2% of the globally emitted CO2 is required to fulfill the current industrial demand. The amount of CO2 emitted is so large that basically despite its extensive use in the industry, you only need 2% of the emitted CO2 to fulfill all the current industrial demand of CO2. It's still a very essential application. You can capture the CO2 from industrial furnaces or power plants and divert 2% of this for these types of industrial uses, but the remaining 98% still have to be stored somewhere else, and it will not have an industrial use in the foreseeable future. Okay. So that becomes a challenge. But first, let us look at how do we capture CO2 from the exhaust of a combustion chamber, whether it's a gas turbine power plant or a coal furnace or an IC engine system. So here then we will start looking at the CO2 capture from flue gases. Now the flue gas is basically a technical term. It's the waste gas after combustion of fuel with air exiting the power plant through the stack. So suppose you are looking at a steam power plant where you are burning coal, and the hot gases are passing through the furnace where it is helping to boil your pressurized water into pressurized steam. The exhaust gases are cooled in the process, and finally it is coming out to the chimney or the stack, and this exit gases, partially cooled exhaust gases, is called the flue gas. This is true for a gas turbine combustor also, as well as the gas that is coming out of the exhaust of a tailpipe in a car or a bus. All of these are called flue gases. The typical composition of flue gas is it contains around 80% nitrogen by mole, 8 to 5% carbon dioxide. So most of the carbon has been burned to produce carbon dioxide. So the CO2 content has increased to from 8% to 5%, depending on whether you are burning methane or oil or coal. The amount of CO2 released will be different, so the fraction changes. In general, 8 to 15% by volume or mole of the flue gas is CO2. Okay. Steam is 6% because the fuel contains hydrogen. That hydrogen burns into steam. So around 6% steam is left. Part of the steam can get condensed also while cooling. So still it may contain some amount of steam. So it contains around 6% steam. Some amount of oxygen is also left over because usually burning happens under what is called lean conditions, excess air conditions. So not all the oxygen gets reacted. So around 2 to 4% of the oxygen originally in air still remains present in the exhaust gases. Then you have the pollutants, SOx, NOx and CO at certain low concentration ranges. So the task we have is to separate out this CO2 from this exhaust gas. It is still a low percent CO2, around 8% to 50%. Most of it is still nitrogen. Okay. Now this variation is somewhat, we need to be careful. It is not necessarily 80%, it can be 70% as well, depending on the CO2 concentration, steam concentration, oxygen concentrations. The total value has to come to 100%. So these values can change as well. Okay. Now how do we capture this CO2 that is present in the flue gas? There are several methods. We will first name these methods and then start discussing them one by one. The main processes of CO2 capture includes capture of CO2 by absorption in certain sorbents. Sorbents are basically chemicals. If you pass the flue gas, the gas through these chemicals, it absorbs the CO2 and the rest of the gases passes through without getting absorbed in that chemical. So this is called absorption in sorbents. That chemical is called a sorbent because it is absorbing the CO2 that is present in the flue gas. Okay. So that is one way of CO2 capture. Another way of CO2 capture is separation via semi-permeable membrane. You pass the flue gas over a semi-permeable membrane at high pressure variance, and the CO2 passes through the membrane while the other gases do not. Then on the other side of the semi-permeable membrane, you get pure CO2 gas and the rest of the flue gas passes away. So that is the capture of CO2 by separation via semi-permeable membrane. Then you have capture of CO2 by electrical desorption using porous electrodes in an electric field. This is kind of a newer technology. We will not discuss this significantly here. Basically, you are using a set of electrodes, porous electrodes, and which are electrically charged, and the electrical charge helps in the separation of CO2 from the flue gas that is passing over these porous electrodes. Okay. Then a fourth method is capture of CO2 by cooling and liquefaction using cryogenic distillation. As we discussed, CO2 can be compressed and cooled to produce liquids or solids, right? So you can basically separate out this CO2 by cooling it and liquefying it, while the rest of the flue gases remain in gas phase, while the CO2 condenses out, and then you can get the pure CO2 out. Okay, so these are the main methods of CO2 capture that are common in the industry today. So the first type of CO2 capture technology that we will discuss is CO2 capture using sorbents. One of the most common types of sorbent used in the industry is monoethanol amine, MEA, monoethanol amine. Okay, it will dissolve only CO2 from cooled and dried flue gas at elevated pressures in what is called an absorber section. Okay, so let us understand what is happening. You are getting the hot flue gas at standard pressure from the stack of your combustor. You are cooling this flue gas to normal temperatures using some sort of a cooling fluid, right? Then you are using a blower to increase the pressure of the flue gas and moving it into the absorber chamber, and you are bubbling this pressurized, cooled and dried flue gas through the liquid monoethanol amine solution. It will absorb the CO2 and the rest of the gas, mainly nitrogen and oxygen, will pass out, right? Then this monoethyl amine, which is now rich in dissolved CO2, is partially expanded and hence depressurized in a Francis turbine. So basically this is a pressurized monoethyl amine. So it's 2.2 bars and 45 degrees centigrade. So this absorbent system works at somewhat higher pressure than a normal atmospheric pressures. Okay, and reasonably low temperatures. Okay. Now what we are doing is we are expanding this monoethyl amine rich in CO2 in a Francis turbine, where some amount of electricity is generated because of the higher pressure. We have discussed Francis turbine before, right? So you have a small version of Francis turbine which is being driven by this pressurized monoethyl amine, which is a liquid, and generating some electricity to run this entire thing. Okay. Then the depressurized liquid monoethyl amine is passing through the regenerator system, which is kept at a 1 bar pressure and at high temperature. So the pressure is falling and the temperature is rising. You are using some heating loops and coils to heat up this monoethyl amine to 110 degrees centigrade within this regenerator system. And when the monoethyl atom is heated up and its pressure is decreased from 2 bars to 1 bar, it releases the CO2 back. And this CO2 is released back into vapor safes and is being extracted out, and hence you are separating the flue gas and the CO2 system. Then this monoethyl amine, which is now been no longer rich in CO2, that is, it has been regenerated, this is compressed and moved back into the absorption chamber. Okay, so that is the main method by which this system works. So CO2 rich monoethanol amine is expanded to a lower pressure and heated so that it releases the CO2 in the regenerator section. The released CO2 is collected while the regenerated MEA is pumped back into the absorption. Depending on CO2 concentration, the most effective sorbent can be different. Monoethanol amine is the most common, but you can use other sorbents as well if the CO2 concentration is different. For example, for a flue gas where the CO2 concentration is high, there are certain things like oxyfuel combustion, etc., where you can get high CO2 concentrations. Solid sorbents based on lithium or calcium can be used. So these are basically solid sorbents based on lithium and calcium. You are passing the flue gas, which is quite rich in CO2, through these sorbents, and the CO2 is being absorbed by these solid sorbents. So that is another possible way of separating out the CO2. This is the most mature and widely used technology in industry today. So CO2 capture by various types of sorbents is the most mature and widely used technology in industry because the costs are low and it's quite effective. Another reasonably well established technology is CO2 capture using semi-permeable membranes. Okay. So here we use CO2 selective metal, polymer or ceramic membranes. So these are specifically selective to CO2 permeation while it prevents other gases from permeating through these membranes. So once again, flue gas is circulated by a blower that increases the pressure to compensate for pressure drop across the membrane. So here you have flue gas at 100 kilopascals. It is passed through a blower which is blowing the flue gas into this semi-permeable membrane reactor. And this is the semi-permeable membrane that you can see here, this dotted section here. Because it is being blown, the pressure at the exit of the blower is higher than the pressure at the inlet, so it's working at higher atmospheres. Okay. On the other side of the membrane, this side, so this membrane is a separator, the pressure exit from the membrane is kept low. Okay, so this 3 point, which is called P2 here, the pressure is kept at 10% of the original atmospheric pressure. So if the original pressure was 101 kilopascals, the P2 here, the exit pressure on the other side of the membrane is around 10 kilopascals. Okay. So this pressure gradient from the high pressure end here to the low pressure end here helps to drive the CO2 gas through this membrane. Because there is a pressure gradient, CO2 would want to drive through that system, while the other gases will want, but the membrane will not allow it. They will act as a barrier for other gases, only CO2 can pass through. Okay. The partial pressure of CO2 on the flue gas side must be greater than the total pressure on the membrane side. This is very important. So, what is being said here is that this gas is CO2 rich, this gas is CO2 lean. Okay. Suppose you are starting with around 15% CO2 and you have increased the pressure to around, say, 150 kilopascals or something. So 150 kilopascals from 100 kilopascals. Okay. So 15% of 150 kilopascals, it's around a little more than 15 kilopascals, say suppose 18 or 20 kilopascals, like that, 22 kilopascals, something like that. Alright. So because the flue gas contains 15% CO2, the partial pressure of CO2 in the flue gas at 150 kilopascals is 150 into 0.15, which is around 22.5 kilopascals. Alright. Whereas here, suppose if this part contains 100% CO2, the total pressure is 15 kilopascals. Okay, 10 kilopascals. So the pressure of CO2 here is 10 kilopascals, whereas the pressure of CO2 here is 22.5 kilopascals. So there is an actual pressure gradient for CO2 itself across the membrane. Without that pressure gradient, you cannot pass the CO2 through the membrane at all. So very important, the partial pressure of CO2 at the inlet of the membrane on the flue gas side must be greater than the total pressure P2 at the exit on the outlet side of the membrane. Okay. This, if it's ensured, you will get a good flow of CO2 through the membrane system. In a single stage operation, CO2 concentration rises from 15% to 45%. So actually, you are still moving some of the non-CO2 gases through as well. Okay. So you are getting around 45% in this final stage here. Okay. Some of the nitrogen, some of the oxygen will go through, but the concentration will increase from 15% of CO2 here to around 45% CO2 here. So what is usually done is a second CO2 selective membrane is put here. We are not showing it in this figure here. A second stage membrane is there downstream of the first membrane, which increases the concentration of CO2 in the final exit of the membrane to around 90%. Okay. Multiple stages are needed for higher separation percentages. So you will need multiple membranes reactors, and the gas will pass sequentially through them till you get nearly pure CO2 systems, CO2 flue gas. Polymeric membranes impregnated with chemicals that allow selective transport of CO2 through the membrane matrix are widely used. So typically polymeric membranes impregnated with certain chemicals that allow the selective transport of CO2 are widely used. At higher temperatures, suppose your installation requires the separation to happen at high temperatures, solvent impregnated metallic membranes are used. Because high temperatures, the polymers will start to melt, so you use solvent impregnated metallic membranes instead, okay, if you are trying to work at high temperatures. So this is also a reasonably well established technology, slightly more expensive and slower than traditional amine absorption technologies. So it is used in many places, but not as extensively as amine based absorption. So next we will look at the cryogenic distillation. So but that will be happening in the next class. So see you and have a good day. So thank you.